Trig, a hot air balloon rising straight out from a level field is tracked by a rangefinder 500 feet from the liftoff point. At that moment, the rangefinder's angle elevation is, at the moment that it's pi over 4, the angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Okay, so I need a picture. So you've got a rangefinder, which is 500 feet from a balloon, and you've got a balloon, which I'm not going to draw, which is some height up in the air, and then we've got an angle there. Okay, so the rangefinder starts out 500 feet from the liftoff point, which is directly, and we're assuming the balloon is just going straight up. And when that angle theta is pi over 4, then the angle is increasing at a rate of, right, so if you had the rangefinder on a tripod, you'd be measuring how fast you would have to be changing its angle. Okay, so angle and time. So here we have d theta by dt, right, the rate of change of the angle with respect to time. And we wanted to determine how fast the balloon is rising. So we are looking for dh by dt. And so what we want to do is just kind of look in the diagram and say, all right, so how are theta and h, and I guess the 500, because that's all we have, related? Because it's related rates, right? So what's the relationship between theta, h, and 500?
Sin theta equals sin over 500.
Let's go with 10.
No.
You sure?
10.
90 hypotenuse. That h is not hypotenuse.
Not that.
So theta, we have opposite, we have adjacent, that's tan ratio. So tan theta is h over 500. Okay, so the idea is let's relate the quantities, then let's take the derivative with respect to time of both sides. So the derivative of tan theta is secant, well, okay, wait, we could play with this a little bit more. Let's do this. So h is 500 tan theta. Okay, might as well do that. Because we want dh by dt. So the derivative on the left-hand side with respect to time is dh by dt. And the right-hand side is 500 times the derivative of tangent, which is sec squared theta. And because we're taking the derivative with respect to time, d theta by dt. Okay, so what do we know? Well, we know d theta by dt. We know theta, right, because the angle is pi over 4. It's at the moment the angle is pi over 4, and we want to find this. Okay, good. So we just have to sub in dh by dt is 500 secant squared of pi over 4. And what was that? 0.14. Okay, secant pi over 4. Yeah, that's what I kind of like to say. Well, secant is the inverse of cos, right? And cos is root 2 over 2. But let's do it as 1 over root 2. Then we just flip it and just get root 2. So it's going to be root 2 squared, which is 2, times 0.14. Secant pi over 4 is like 1 over cos. Let's throw that over there. So that's going to be 1,000 times 0.14, which is 140. Now it's a change in height with respect to time, and we've got feet there, so it'll be feet per minute. Yeah, right. Sorry. Wouldn't mind seeing a hot air balloon going 140 feet per second. Yeah, I don't know you'd necessarily want to be in it. Okay, 140 feet per minute. That's 12. 13. A boat is pulled toward a dock by a rope through a ring on the dock 6 feet above the bow. The rope is hauled in at the rate of 2 feet per second. Determine how fast the boat is approaching the dock when 10 feet of rope is out, and determine the rate between the angle between the rope and the dock is changing when 10 feet of rope is out. Okay, so we need to start with this with a diagram. Really should have been provided with one in the first place, but I'll do my best attempt at a diagram. So we're going to have a boat. There's the boat, and it's being pulled towards a dock, and there's a ring at the top of the dock, and then there's this rope. Okay, and this is 6 feet. Okay, so a ring on the dock 6 feet above the bow. Okay, and then here's the dock, and then here's the rope, right? And so the rope is being pulled in here. The rope is hauled at a rate of 2 feet per second. So let's call this L, so that'll be the length of the rope. Okay, and we'll call this H, because it's the height that the dock is above the bow. And then we'll just call this X. So determine how fast the boat is approaching the dock, so that's the change in X, right? So we're looking for, so in terms of this diagram now, how fast the boat is approaching the dock, that's going to be dx by dt. The rope is being hauled in, so that's dl by dt, right? The length of the rope is changing. Okay, now initially it's 10 feet. So by the Pythagorean theorem, we can say that L squared is equal to h squared plus x squared. Or let's say x squared plus h squared. And we know h, right? H is 6. So just put 6 in there. So L squared is x squared plus 36. Now, we've got dl by dt, we want dx by dt, so we're good as far as this, right? We should now be able to take the derivative, because all we've got is the L and the x. Okay, so derivative left side, we'll get 2L. Now, we do have a choice. Since it's dx by dt we want, we could rearrange that to go x squared is equal to L squared minus 36. Won't make any huge difference. So 2L times dl by dt is, and then this side is going to be 2x times dx by dt plus 0. Okay, 36. And what do we want? We want a dx by dt. Okay, so whoops, just rearrange it a bit. So dx by dt is going to be, we'll just divide both sides by 2x. So 2L divided by 2x times dl by dt. Okay, 2's go away. So we need L, we need x. Well, we know L because 10 feet of rope is out. We know dl by dt, right, because that was given. So we need to figure out what is x when L is 10. So squeeze this up here. So when L is equal to 10, then x squared is equal to L squared minus 36. 100 minus 36, 64. X is 8, right? Or you know your 3, 4, 5 triangles and say, hey, that's just a 6, 8, 10. Right? It's variant of the 3, 4, 5. Okay, so we got everything we can fill in here, right? So dx by dt is equal to L, which is 10, divided by x, which is 8, times dl by dt. Okay, 2 feet per second, but what's happening to the rope? Is it getting longer by 2 feet per second or shorter?
Negative.
Right, so that rate of 2, the rope is hauled in, means that dl by dt is equal to negative 2 feet per second, right? It's getting shorter. right? So the balloon was getting higher, that's a positive, right? The angle is going up. If the balloon were descending, it'd be coming down. Okay, times -2. Was it 5/2? Yeah. -5/2 feet per second, right? So it's a change in the distance, so the boat is approaching, getting closer to, right? So that's the -5/2.
Well, but if the question is how fast it's approaching, then how is it quickly approaching in a negative manner?
Because its distance is getting shorter.
Oh, okay.
So the x value is getting smaller.
Okay. I think with 2L
It's
over
a vector
2x, and we need 2x over 2L.
Okay, so this is what I'm isolating. So I'm dividing by this. So it's 2L over 2x dl, and then I'm reversing the signs. Sorry. Should maybe have solved this for x in the first place, right? Because it really doesn't matter where the 36 is, that derivative is just...
Yeah.
What else? Oh, determine the angle between the rope and the dock. So this angle is going to be up here, right? We have the little angle theta between the rope and the dock. And we want to know the rate at which the angle between the rope and the dock is changing when 10 feet of rope is out. Okay, so having labeled this with theta, we want d theta by dt. Okay, so we have a couple of choices. Right, and if we want, we can isolate the diagram a little bit here and say, okay, so that's theta, and this is 6, and this is 10, and this is 8. Okay, that's like x, and that's like L, and that's like H. Okay, so this is what we're working with, right? And we want that when L is 10. Okay, so that's really what we're working with, right? So we've got the 10, the 6, and the 8. We've got that theta. So how are we going to relate theta with x? Because remember, x is changing, right? H is constant. L is changing and x is changing. So theta is, okay, so opposite over hypotenuse, right? But we don't want to do it with the x, really. Well, okay, hang on. So we don't want it, the L is changing. So let's do it with H and x. So we'll go tan theta is opposite over adjacent. So tan theta is x over h. Okay, so call that x over 6, right? Because we know x is changing.
Shouldn't you use the values that are not calculated in the
Well, the only value I have is 6, which is a constant.
No, but it says you have 10 feet of rope, so you
Yeah,
know the
that's why I'm not going to use the 10 for this. Okay. I want to use it in terms of the 6, which is always constant, right? That 6 never changes. The L is changing, okay, and the x, but we know the rate of change of the x, right? So, I mean, we can actually do this a couple of ways, right? You can do, so, well, let's just finish this. So, take the derivative of both sides with respect to time. So derivative of tan is secant squared. So sec squared theta d theta by dt is 1/6. Right, that's the constant. Dx by dt. Okay, we want d theta by dt, right? So we're just going to divide by secant squared. But you could just multiply by cos squared, right? Secant's 1 over cos. So to isolate d theta by dt, we'll go, well, let's go 1/6 times cos squared theta times dx by dt. Okay, and now we can fill in, right? So d theta by dt is 1/6 cos squared. Okay, so at this moment, when we have the 6, the 10, and the 8, what is cosine of theta? It's going to be 6 over 10, right? So this diagram is at the moment when we have the 10 feet out. So cos theta is 6 over 10, or 3/5. Okay, so let's not write that in. Let's put in 3/5 squared. And dx by dt we worked out, right? So that's negative 5/2. Okay, so that's from here, right? So from part A. And all we're going to do is do that, right? So what do we got? 9. Well, let's go 1/6 times 9/25 times negative 5/2. 5. 3. So we get negative 3/20. Okay. Now it's a change in angle. Angles are measured in radians, so it's radians per second in this case. Radians per second. So up here we did the angle in terms of x and the 6, but we could also do it in terms of the L, right? So I'm just gonna, I don't know if I want to show the whole thing, but we'll show the start of, so part B, or relate L and theta. Okay, so if we go to relate L and theta, right, then we've got theta here. We've got L and we've got the 6, right? 6 is 6. L is going to change. So theta, we got L, we got hypotenuse over adjacent, which would be the secant, right? So secant theta would be L over 6. So secant theta is L over 6. Okay, and then you do the derivative. So you just do what we did there, right? But instead of tan, you're now doing secant. Okay, so the derivative of secant is sec theta tan theta. So sec theta tan theta d theta by dt is equal to 1/6 dl by dt, right? Now remember, that's a known quantity, right? We know that the rope, that's the rate of change of the rope. That's the -2. So here, we were using a calculated, I mean, this value is exact, so, right? Here by using dx by dt, that was a value we calculated in part A, and you sort of said, hey, can we stay away from that? So, yeah, we can. We stay away from it if we just do it in terms of L. And then we've got the dl by dt, which was given, and so you're going to have to multiply by, like, cosine cotangent, and I'll get rid of this side, right? So that d theta by dt would be, let's do 1/6 cos theta cot theta dl by dt. And then you could just fill in the values, right? So 1/6 cosine, where we figure that out, was 3/5. So cotan's got to be like 4/3, 3/4. I'll never move that back up again. 3/4 and -2. Okay, so 2, 3 and 6. We got -3/20 radians per second. Good thing too, right? Okay, so that's an alternate, right? You can relate L and theta, or you could relate x and theta. A beacon. Wait, I missed one.
No, that's it yet.
Yeah.
14.
Where's 14? I don't know.
Yeah, no, but I'm not sure if anybody's told you, but you missed 14 here.
Yeah, I know that. I can't find 14 here.
Better not write it down. You're welcome.
All right, well, you've read that over 15 times now. So, let's just start with a diagram. So we've got a side of 15 meters, and we got a side of 20 meters, and we've got an angle between the two sides. And that angle is increasing at a rate of pi over 90 radians per second. And we want to know is, okay, we got this third side, and how is its length changing? Okay, so how is the length of the third side changing when that angle is pi over 3? Okay, so let's call the third side x. Then what's x? How do we relate x and theta? Cosine, yeah, or law of cosine. Okay, so we're going to use the cosine law, which says that a squared, so in this case x squared, is equal to a squared plus b squared minus 2ab cosine, or theta. Okay, so we can work this down a little bit. So 15, we know how to square a number ending in 5 now, right? Take the number in front, multiply it by the next higher number. 1 times 2 is 2, and then it ends in 25. And 20 squared is 400, and 30 times that is 600. Cos theta. So a little bit more, so we get 625 minus 600 cos theta. Okay, so there's our relation. We want dx by dt, so that's good, we got x squared, so we can just take the derivative of both sides. So we get 2x dx by dt is equal to 0 minus, so I don't need that 0 there. So, okay, we've got minus 600, so that's going to be minus 600 cos is a negative sign, so it would be plus. So just 600 sine theta d theta by dt. All right, that's pretty much everything we need, right? I mean, well, okay, no, we got to get rid of that 2x, I guess, right? Okay, so let's write out the 2x, so we get dx by dt. So let's go 1 over x. Well, what's going to happen? Be 300. 300 over x times sine theta d theta by dt. All right, so what do we need? Well, we need x. And so we're going to have to figure out x. And we need x when the angle is pi over 3, right? So we're going to have to basically just kind of work this out for pi over 3. Okay, so going over here and start, so we got x squared is 625 minus 600 cos of pi over 3. So x is the square root of 625 minus, okay, so cos of pi over 3 is that a half? Is that a half? Yeah, it's half, right? Okay, so this would be 625 minus 300. So the root of 325, 25 goes into that. 4 is 100, 8 is 2, 13 times, so 5 root 13. Okay, so dx by dt is 300 divided by 5 root 13 times the sine of pi over 3 times d theta by dt, and d theta by dt is pi over 90. All right, what's the sine of pi over 3? That's like root 3 over 2, right?
Can't you divide the 300 by 5?
I can. I can divide the 300 by 10 and get 30, and I can divide the 30 by 90 and get a 3. And I can get rid of the radical sign on the bottom and go root 39 pi over 39. And What is that? It's going to be meters per second, right? Because it's the length of the third sine. Meters per second. Which, if you had a calculator, works out to about 0.5 meters per second. It's about a half a meter per second. Okay, and there's the whole thing. Yet again. And now, the real 15. A beacon located a perpendicular distance of 300 meters from R on a straight shoreline revolves at a revolution of revolves at 1 revolution per minute. Determine how fast its beam sweeps along the shoreline at the point 500 meters from R. Okay, so here, let's say we have a shoreline here, and here's point R. And the beacon is located 300 meters perpendicular distance. So 300 meters. And the beacon has a light that is sweeping, so we'll see the light sweeping across here. And we want to know when it's at a point 400 meters from R. So let's complete that, and let's throw an angle in there. So the 1 revolution per minute is going to be our d theta by dt, right? But what's 1 revolution per minute? 2 pi radians per minute, right? So 1 revolution per minute, this is 2 pi radians per minute. Okay, and what is that? That's d theta by dt. Okay, so we can relate theta and the 300, or no, sorry, what do we want? How fast its beam sweeps along the shoreline. All right, so let's pick up 400 right now. Let's just call that x. Right, and we want to do that when x is 400. How fast is it sweeping, right? Okay, so we've got a nice little tangent there, right? We've got theta in the bottom, we got opposite and adjacent, so tan theta is x over 300. And the derivative, so we take the derivative, we're going to end with dx by dt, but that's fine, that's what we want, right? The rate that it's moving across this way. So sec squared theta, d theta by dt, is 1/300 of dx by dt. So we want dx by dt, so let's just multiply both sides by 300. So dx by dt will be 300 secant squared theta d theta by dt. Okay, so what do we know? Well, we know that we want x to be 400, right? When x is 400. So when this is 400, and we need the secant, which is the inverse of cos, so we need that. What's the hypotenuse going to be? 500, right? 3, 4, 5 triangle. So through 500. Okay, so sec squared theta. So it's 1 over cos. What's cos? This. Well, or what's sec? It's going to be 500 over 300, right? Or 5 over 3 squared. Okay, so this will be 300. Secant will be 5/3, and that's squared, and then we've got the 2 pi for d theta by dt. Okay, 300 times 25 over 9 times 2 pi, 9, 3, 2,500. What do we got? 2,500 times 2 is 5,000. So 5,000 pi over 3. And what units were meters? Meters per minute? Meters per minute. Okay, 5,000 pi over 3 meters per minute.
About 5,000 meters per minute.
Yeah. That's not a pi cube. 3. Okay. Yeah, a little over 5,000 meters per minute. That's that. So in these guys, draw yourself a diagram, angle, figure out how things are related. What rate did they give me? What rate do I need to find? Set it up. Derivative both sides with respect to time.